For this work, we're trying to take the derivative of a chain rule problem. And in this case, we've got a function of more than one variable. So these tree diagrams will allow us to keep our thoughts organized as we try to form up what these larger chain rule problems look like. So let's just note we have a function of x and y, and those two functions then are functions of a third variable t. So here's our chain rule. And we also recognize that we're going to need to take some partial derivatives here. So let's go ahead and start to set up this tree diagram. And some books will write this out vertically, some will write it out horizontally. It really doesn't matter which way you do it. It's just a matter of keeping our work organized in a way that we don't miss a particular product that we need. So we've done this in terms of z here, so I'm going to write it out that way when we start laying out our tree. And of course, as a function of two variables, we know we're going to have to take partial derivatives. So this first branch is going to represent the partial of z with respect to that x variable. The bottom branch is the partial of z with respect to the y variable. So this represents our two derivatives of the outer function. Of course, with chain rule, we have to multiply times the derivative of the inner function as well. So for each of these, we make another branch. And now we take the derivative of the inner function with respect to the same variable that we did here. So we took the partial of z with respect to x, and now we need to multiply times the derivative of x. So this upper branch then becomes dx dt. And likewise on the lower branch, here I took the partial with respect to y, so the derivative of the inner function there would be the derivative of y, dy dt. So now we just go ahead and multiply through to form up the individual chain rules. So this is the partial of z with respect to x times dx dt. And on the lower branch, we have the partial of z with respect to y times dy dt. And now to form the overall derivative, dz dt, we just add those two quantities together. So we get the partial of z with respect to x times dx dt plus the partial of z with respect to y times dy dt. And there we have the formula for our derivative for this particular scenario. One thing to point out maybe is just that if we look at a little cancellation, we have a couple of derivatives with respect to x, or derivatives with respect to y. You see that we end up with dz dt effectively, aside from the partial derivatives, we end up with dz dt for both of those, which is what we really want to create. And then the sum of those individual dz dt's gives us our overall derivative. It's just kind of a way to keep track of what you're doing if you're not using a tree. We know that as we form these individual products here using the chain rule for each side, we've got to make sure we account for all of those. And then we also want to make sure that we're multiplying up to whatever the notation is for our derivative. So now that we have a method for organizing these chain rule type problems, when we want to expand to say a function f of x, y, and z now maybe, where these are all individually functions of other variables, maybe they're functions of two variables, it really just amounts to making a larger tree as we go through and organize all those derivatives of inner functions over and over and over again. So it just becomes a larger and larger chain rule problem.